Good morning everyone. In the last class we discussed about various types of FGMs, that is porosity gradient FGM, chemical composition FGM and microstructure gradient FGMs. So depends upon the various processings we are going to manufacturing those all types of FGMs. So processing of FGMs are classified into two types, that is thin FGM and bulk FGM. So according to the process of manufacturing, those are classified into two types, that is thin FGM and bulk FGM. So here, if the size of the material, if the size of the FGM is less than 1 mm, that is considered as thin FGM. Whereas if the size of the FGM, the component is more than 1 mm, then that is called bulk FGM. So thin FGM comes under coating for the other components. So as you have seen that many of the components are coated with nickel, magnesium as well as chromium for their applications. So those coatings will be eroded over a period of time during applications. So during application, due to lack of bonding between the bare material and this coating, those materials will be vanished out. So to avoid that and to increase the life of the component, here those materials are made up of functionally graded materials. So due to usage of these functionally graded materials, that will have good bonding with the core material, and on the other side it will give the desired property. So generally to improve the wear resistance, we are going for chrome coating. So so to improve its wear resistance, we are going for FGM material. So the FGM material on one side it should give good property, on the other side it should have good bonding with the base material. So the base material is the main component. On the top of that we are going to add one more layer, that is called thin FGM. So that is thin FGM. It consists of relatively thin sections or thin surface coatings. So if the size of the component is less than 1 mm, those are also considered as thin FGMs. So if the size is more than 1 mm, so it means greater than 1 mm, then those are called bulk FGMs. So for bulk FGM, the definition is bulk FGMs are those with thickness, the thickness greater than 1 mm. If the thickness is greater than 1 mm, this requires, greater than 1 mm, that is called bulk FGM. And this bulk FGM, this requires more labor intensive process. So the production of this bulk FGM products are more labor intensive process. So it requires high labor for production of these composites, of these materials compared to regular materials or regular components. Next, processing techniques. So to produce thin layers as well as bulk FGMs, we are having different methods. So depends upon the material and depends upon the component application as well as the profile of the component, we are having various methods. So as we know that depends upon the complexity of the component, we are having various manufacturing methods. So if we call back to the metal manufacturing methods, so depends upon the size, we will go for single pattern castings or multi-piece castings. So that is depends upon the complexity. Here also depends upon the complexity of the job, we will have different materials, different manufacturing processes. So we are having various thin forming processes. That is, for the formation of thin FGMs, we are having various methods. That is vapor deposition techniques. So in this vapor deposition technique, we are converting the phases in the form of vapor and we are depositing the material onto a substrate, onto the target material. Onto the substrate material. So here I want to deposit some amount of layer. So we are converting the base material into vapor form and we are letting the material to deposit on the core material. So that is, here we are converting the material into vapor state. So vapor state and we are depositing on the component. So those processes are vapor deposition processes. That is, there are two processes. Generally we are using CVD or PVD. So CVD stands for chemical vapor deposition and PVD for physical vapor deposition. So depends upon the material Depends upon the properties of the target material, we are having various methods. That is CVD or PVD. So similarly, we are having one more process. That is plasma spraying. So here the material is exposed with high temperature. We are letting the component to be deposited. So in detail we will discuss about this process. Next, one more process is self-propagating high temperature synthesis. So that is self-propagating high temperature synthesis. So this is an exothermic material process. So the next, ion beam assisted deposition, that is IBAD. So generally in the short form it is called as IBAD process. Ion beam assisted deposition. So similarly for bulk components, it means if the size is greater than 1 mm, those are considered as bulk FGMs. For the production of bulk FGMs, we are having various methods. That is powder metallurgy, and the next one is centrifugal method, and the next one is solid freeform fabrication. So these three are the commonly used methods for forming of FGMs for bulk materials. For thin, we are having four methods. That is vapor deposition technique, plasma spraying, self-propagating high temperature synthesis. The next one is ion beam assisted deposition. So these four methods for thin FGMs. Next, for formation of bulk FGMs, we are having three methods. That is powder metallurgy, centrifugal method, and the next one is solid freeform fabrication. Solid freeform fabrication is also called as 3D printing. So here we are going to use 3D printing techniques. That is rapid prototyping techniques. So now coming to the first one, chemical vapor deposition. So here, as we discussed that, so these methods are used for forming of thin sections on the components or for thin components itself. So here the film. So as we know that film means the thin layer. So film is formed by chemical reaction between gaseous compounds. So by means of chemical reactions between the gaseous components, the reactant will form on the substrate and it will give one more material. Next, so this is the schematic of chemical CVD process. So here the complete process to be done in a vacuum chamber. So this is a reactor. So here, so the blue color one, this is the substrate material. So the complete blue one is the substrate material. So on this substrate, and it means this is our component. On this component, we need to deposit our FGM. So our deposited material should have good bonding with this material, and it should give better properties on the other side. So for this purpose, here we are generating a FGM thin film. So for that purpose, here this chamber consists of two valves. That is inlet one. From here we are inletting the gas, and here one more, that is to pump. So the reactants, here, so during this chemical vapor process, so some amount of reactants will be generated. So those reactants will be sent out to pump by means of this outlet valve. So here this consists of two valves, that is one inlet and one more is outlet. So the reactant gas will enter into this chamber by means of this gas inlet, and the reactants, the byproducts will be generated after these reactions. So those byproducts can be let out from this outlet. It means to pump. So an external pump sucks all these byproducts. Those are reactant byproducts are extracted by means of this pump. So this is the substrate. On this we are going to add material. So by means of this gas inlet, we are passing the reactant gas. So the material which to be deposited on the surface is passed from this material. The material in the form of small atoms will bombarded or will come into the chamber, and it will react with the substrate material. So the reactant material, this is the substrate material. So that will react with the substrate material and it will form one more material during reactions. some amount of byproducts also generates. So the main material will be deposited on the substrate and the byproducts in the form of gas will be let out into the outlet by means of a pump. So chemical vapor deposition is a chemical process. So this is a chemical process used to produce high purity. By means of this CVD process, we can get high purity and high performance solid materials. So compared to other process, by means of this chemical process, only the reactant materials only will be deposited on the surfaces. So that only the pure materials will be deposited and the reactant gases, it means the excessive material, the reactant byproducts will be let out. So that only the pure materials will be left over on the component, so that we can get high purity and high performance materials. The next, in a typical CVD process, the substrate is exposed to one or more. So it is exposed to one or more volatile precursors. So it means, so those precursors are entered into this chamber by means of this gas inlet. So if it is exposed to one volatile material, one material only, then that is a monolithic material. So here from this gas inlet, so depends upon the time being, we are going to change different composition materials. So that different layers will be deposited. As we seen in FGMs, so the layer by layer, the composition is changing. So by changing the various compositions of the inlet material, it means the gaseous material, we can get different materials. So that if it is having different phases with different materials, then the property will vary. So different materials in the sense, different composition materials. So exposed to one or more volatile precursors which react. So all the materials should react with our substrate, which react and decompose on the substrate surface to produce the desired deposit. So to get the desired properties, we are passing one or more volatile precursors. So depends upon the functionality, we can add different materials. So during this process, so as we discussed that, so some byproducts will be generated. So during this process, volatile byproducts are also produced. So which are removed by gas flow, through the reaction chamber. So this is the gas flow out. So due to along with this gas outlet to pump, those reactant byproducts will also leaves from the chamber. That is CVD process. Now PVD process, physical vapor deposition. So here PVD is characterized by a process. So by a process in which the material goes from a condensed phase. So the material goes from a condensed phase. So this condensed phase, in the sense, it might be a solid or liquid phase. So the physical state, so it might be in the form of solid or physical. The condensed phase to a vapor phase. So we are converting the regular solid or liquid state to vapor phase, and then back to the thin film, and then back to the thin film, condensed phase. So this is the schematic of this. So initially the raw material is in condensed form. That is, either it might be a solid or liquid. So after supplying heat, so by supplying the heat to this material, so by gaining the temperature to the material, it will convert into vapor form. It means by means of this thing, it is converting into vapor form, that is gaseous phase. So after converting this into gaseous phase, it is again depositing on the surface. So this gaseous phase is transported by means of transportant gas. So generally this transport gas is inert gases. So these inert gases, so this is schematic. So those inert gases will take material from the target material and it will deposit on the substrate material. So here, so those gases will be transport to the solid phase onto a substrate. So this is the schematic of PVD process. So here so the yellow color one is our final component. So this is our substrate material. On this substrate we are going to deposit one more material in the form of, that is in the form of thin film. That is our final FGM. So here we are going to deposit material on the substrate. So the material to be deposited is our target material. So on which it is going to deposit is substrate, and the material which is going is the target material. So it means here we need to transfer this material onto the surface of this material. So initially the phase of this material is solid phase. So that is condenser phase. So by supplying the heat, this material will be in the state of vapor, will be converted into vapor phase, and those vapor atoms is transported by means of transporting gas. It means inert gases. By passing the inert gases, so those inert gases will bombard on this surface, and it will take this atom and it will strike to the substrate material. So this sputtering gas. So here we are passing the inert gases. That means the transporting gas. So here the transporting gas atoms will move towards the target material, and it will take the target material and it will deposit on the substrate material. So here we are, by means of heat, it is converting into vapor phase. So this transport material will catch the vapor material, and it will deposit on the target material. It will deposit on the substrate material. The final substrate, the metal which is depositing is target. So here, by means of sputtering gas, we are transferring from the target to the substrate. So here we are transferring from target to substrate by means of transporting gas. So initially it is in the form of, it is condensed state, which is in the form of solid or liquid. After supplying heat, it is converting into vapor. Those vapor atoms will be let into deposit on the substrate, and it allows to cool. That is solidification. Finally, we are getting it in the solid phase. So, physical vapor deposition is fundamentally a vaporized coating. So, PVD, physical vapor deposition is fundamentally a vaporization coating technique. So, it is a vaporization coating technique involving transferring of material at atomic level. So, at atomic level, we are transferring the material from the substrate. We are transferring from the target material to the substrate. The process is similar to chemical vapor deposition. So, in the earlier slides, in the earlier session, we discussed about CVD process. So, this process is also similar to CVD, except that the raw material precursors. So, here we are using the raw material in the form of condensed state, that is either solid or liquid state. So, on the chamber itself, we are placing the target material. So, the atoms, the sputtering gas is used to, it means the transporting gas is used to transfer the target material onto the substrate. So the same thing, here we are transferring the target material to the substrate material, whereas in chemical vapor deposition process, we supplied separate gas. That gas is reacting on the substrate surface, and it is depositing. So except the transferring gas, except the reacting gas, everything is similar to CVD process. So the process is similar to CVD process, except that the raw material are precursors. It means the material that is going to be deposited starts out in solid form. The metal to be deposited is in solid state. Here it is in solid state. It is in the form of, it is condensed form. Whereas in CVD process, that is a gas. The gas is reacting with the substrate and it is depositing. So the metal is going to deposit, starts out in solid form. Whereas in CVD, the precursors are introduced into the reaction chamber in the gaseous state. In the gaseous state, we are passing the gas into the reaction chamber. The reaction chamber we are passing in the form of gaseous state. That is CVD process. That is PVD process. Next, one more process, that is plasma spraying. So here the powder material is exposed to high temperatures and the material is letting to deposit. It means the metal is sprayed on the composite so that a thin film is depositing. So this is the working process of the component. So here the last one. So this is our substrate material. So on the top of this we are going to coat our FGM. So here the plasma gas, it means high temperature gas. So along with that powder material, so here the powder is injecting in this direction. So from this nozzle the powder is passing. So by means of this anode and cathode, an arc is generated. So an arc is generated and that is passed through a plasma gas. So this gas is pushing this arc so that high temperature gas will be letting out from this nozzle. So and from one more nozzle the powder is coming out. Those two are mixed together and those are deposited on the substrate. So here hot gas is coming from this chamber by means of this anode and cathode. As we know that as the fusion welding, arc welding. So between anode and cathode heat is generating. So similarly here also between anode and cathode. So here it is the anode material and this is the cathode material. Between these two materials arc is generated. It means and those fire, that heat is transferred by means of the plasma gas. By means of this plasma gas we are pushing the powder onto a substrate. So due to this temperature the powder is getting the temperature, gaining the temperature and it is converting into voltaic form and it is depositing on the surface of our component. So this is spray stream of molten particles. So here the particles is converting into molten state, that is by means of this hot gas the powder is converting into molten state. So this is a spray stream of molten particles. Next. The plasma spray process is basically the spraying of molten or heat softened material. So this is the way working of our plasma spraying. So here it consists of a chamber. This is a powder chamber and it is having one more pipe. Through this pipe the air is coming, the plasma gas is coming and through this chamber the powder is coming. Both together is going to spray on the component. So both together, the gas as well as the powder. So this gas is letting or pushing the powder materials onto the substrate. So due to this gas, the powder is converting into molten state. So that the liquid or molten material is depositing on the surface. So the plasma spray is basically the spraying of molten or hot softened material on a surface to be provided a coating. So here gradually we are changing the composition of the powder. So as we know that if it's an FGM, so that if we change the composition layer by layer, it means the phases by phases, we are getting a different material that is called FGM. So here initially if we take a 100% of a material, after that gradually we are changing the composition of the material. The process is same, but we are repeating n number of times to get different materials. It means different composition on the substrate. So material in the form of, so the process, material in the form of powder is injected into a very high temperature plasma flame, onto a high temperature plasma flame, where it is rapidly heated and accelerated to a high velocity. As we know that the gas is coming. So from here the plasma gas is coming. The plasma gas So the plasma gas is coming in this direction with high velocity and the powder is coming in this direction. So the plasma is due to this plasma flame, the powder metal is converting into molten state. So high temperature plasma flame where it is rapidly heated and accelerated to a high velocity. Due to high velocity of this plasma gas, our powder is also moving with high velocity. and due to this flame, our material is converting into molten state. That is, by means of this flame, it is rapidly heated and accelerated to a high velocity. The next, the hard material impacts on the substrate surface and rapidly cools, forming a coating. The hard metal impacts on the substrate surface. So this is our substrate surface. That is impacting on the substrate surface and rapidly cools, forming a coating. So and then finally we are getting a coating on the surface. The coating is our thin FGM. The next one is self-propagating high temperatures. So self-propagating high temperature synthesis. So here, so this is similar to powder metallurgy process. Here the raw materials, the required material is mixed with some exothermic material. So some synthesis material, some exothermic material. So it is mixed together with. So this is our main raw material. This is our main raw material having different compositions. So those are mixed with an exothermic material all together. After that, those all together placed in a die and those are pressed. So it depends upon the size as well as shape of the component. Those powder is filled onto a die and those all are compressed. So after that, finally we are getting the compound. So this compound consists of our raw material as well as our exothermic material. Those materials, by means of the pressing, we are getting a compound. After that, by means of heater, we are igniting this exothermic material. So by igniting the exothermic, a wave form of light, a 5-wave will pass to the component, and finally, after cooling, it will get a final compound. So finally, we are getting a compound after this synthesis. So self-propagating high temperature. So the temperature of the metal. So initially, the temperature. By means. So this is our component. So by means of igniter. So we are letting a component on the top of the component, so that the fire will start initiating and then it will propagate in the downward direction. So that cooling rate will varies from the top side to the bottom side, so that the microstructure variant can be obtained by this process. Similarly, so by changing the size of this exothermic material, it means the composition of the exothermic material from top to bottom, we can get different porosity gradient. So here we can get the microstructure as well as the porosity gradient. So the microstructure gradient FGMs can be achieved due to its thermal equilibrium. So here, during its cooling, so due to variation in its cooling rate, we are getting different microstructure compound. So by means of this igniter, we are getting a spark on the top of the compound, so that a combustion wavefront will start and it will move in the downward direction. So igniter, and this is a product, and it means this is our final product, and so this reaction fluid. So this the circle is the combustion wavefront. So before heating and after heating, so there is a variation in cooling of this compound, so that we can get different microstructure compound, right? So now self-synthesis. So self-propagating high temperature synthesis. So in its usual format, SHS is condensed starting from finely powdered reactants that are intermediately mixed. So these finely powdered reactants. So finely powdered reactants is none other than our exothermic materials. So those are mixed with our component. So are intermediately mixed. So next, in some cases, the reactants are finely powdered. So in some cases, the reagents are finely powdered, whereas in some other cases, they are centered to minimize the surface area. So to minimize the surface area and prevent uninitiated exothermic reactions, which can be dangerous. So if all the exothermic material will be ignited at the same time, it might be a danger. So to avoid this dangerous, so they are minimizing. So they are minimizing by means of this centering. So they are centered to minimize the surface area and to prevent uninitiated exothermic reactions, which can be a dangerous material, which can be dangerous to human health. The next, the synthesis is initiated by a point heating. So the synthesis is initiated by a point heating by means of an igniter. It means by means of an igniter, a point initiation, the point flame will be initiated. The synthesis is initiated by point heating of a small pot. So usually the top. So on the top of this we are having an igniter. So by means of this igniter we are igniting the small portion of the pot. This small pot. So point heating of a small pot. Once started, a wave of exothermic reaction sweeps through the remaining material. So this green color one is a combustion wavefront. So it will initiate and it will move towards the compound. So that we can get different microstructure compound. That is our FGMs. So next, the last one is ion beam assisted deposition. So this process is also similar to chemical vapor deposition. So by means of ion bombarding, we are depositing the material onto a substrate. So here it consists of a substrate material and so here it consists of an ion source. So by means of this ion source, the materials will be bombarded from a target material to a reactant gas. So it is similar to chemical vapor process, but by means of ions, the material is bombarded onto the surface of the substrate. So these are the various processing methods of tin FGMs. So today we discussed about 4 FGM methods for the formation of tin FGMs. That is vapor deposition process, that is chemical vapor deposition and physical vapor depositions. So by means of different vapor techniques, so we are converting by means of different vapor techniques, we are depositing a thin film of FGM on the surface. Next, by means of high temperature synthesis, we are igniting the exothermic material and we are getting different microstructure component. So if the microstructure is varying from one portion to other, so the component will give different properties on different sides. The next one is by means of ion bombarding. So by means of ion bombarded, we are depositing a component on the surface of the component. So these are the various types of FGMs. Those are functionally graded materials. Thank you.